Right now, billions of dollars disappear into heating bills every winter, while perfect thermal conductors sit crushed in recycling bins, waiting to be forgotten. Aluminum cans, the same material engineers prize for heat transfer, are thrown away by the ton. But the real shock is this. In the 1970s, this technology came dangerously close to going mainstream. And then, somehow, it was pushed back into the shadows. Quietly, deliberately. What sits in your trash could become a heating system that costs almost nothing and cuts your bills for good. But this story does not begin in some sleek modern lab. It begins in Geneva in 1767, when a Swiss scientist named Horace Benedict de Saussure built what he called a hotbox. Nothing fancy. Just simple wooden containers lined with cork and covered with glass. That was it. He placed them under the alpine sun and watched the thermometers climb. 230 degrees Fahrenheit. Hot enough to cook food, hot enough to prove something enormous. Sunlight, once trapped, turns into thermal energy through what we now call the greenhouse effect. That discovery was not vague theory. It was observable, repeatable, undeniable. Scientists across Europe repeated those results for decades. The physics was proven. The practical uses were obvious. But somehow, despite all of that, it would take nearly 2 centuries for this knowledge to reach the object sitting in your recycling bin right now. Then came 1891. An American inventor named Clarence Kemp filed a patent for something revolutionary, the Climax solar water heater. Black painted tanks placed inside glass-covered boxes and mounted on rooftops across Southern California. No electricity, no fuel, just sunlight and clever engineering. By 1897, nearly 1/3 of all homes in Pasadena, California were heating their water with the sun. Then, in 1909, William Bailey improved the design with a thermosiphon system. And this is where the story becomes impossible to ignore. Hot water rose naturally into insulated storage tanks. Cold water flowed back down to be heated again. No pumps, no motors, no operating cost. The system worked day after day with nothing but sunlight and gravity. By 1941, more than 50,000 homes in Florida alone were running on solar thermal energy. Families in Miami and Tampa had hot water and supplemental heating while paying nothing to utility companies. This was not experimental technology. This was not fringe science. This was functioning infrastructure serving tens of thousands of American households. And then, the eraser moved in. After World War II, natural gas pipelines spread across the nation. Petroleum companies, swollen with wartime profits, pushed aggressively into state legislatures. Building codes began to change. Homes suddenly needed gas lines, furnace rooms, ventilation systems, and installations that only licensed contractors could handle. Solar thermal research lost funding. Patents were bought and locked away. In Florida, the solar water heater industry collapsed within a decade as artificially cheap natural gas flooded the market. An entire generation grew up without ever realizing their grandparents had once built working solar systems on their own rooftops. The knowledge did not disappear because it failed. It disappeared because it threatened the wrong balance sheets. But the physics never changed. Then came 1973, and the Arab oil embargo forced Americans to remember what had been buried. Heating fuel shortages spread fear across the country. Gas station lines wrapped around blocks. Thermostats in homes across the Northeast dropped to 55 degrees Fahrenheit. Families in Minnesota and Michigan stared into winter without knowing if they would have enough fuel to get through it. And in garages, sheds, and workshops across America, backyard inventors started experimenting again. Not with luxury systems, not with expensive materials. With whatever they had. They tried sheet metal. Copper tubing, old radiators, painted black. But one design rose above the rest because it used something almost every household already had in abundance: aluminum beverage cans. That was the breakthrough hidden in plain sight. Hollow cylinders that naturally channeled airflow. Aluminum that transferred heat with remarkable efficiency. The supply was effectively endless. Every week, every house produced more of them. And the numbers backed it up. Aluminum conducts heat about 5 times better than steel. That was not just convenient. It was almost perfect. Mother Earth News published construction plans for PopCan solar heaters in 1977, and tens of thousands of readers built them that very winter. Then reports started pouring in from Vermont to Colorado. Output air temperatures rising by 30 to 40 degrees Fahrenheit. Rooms warming noticeably on sunny winter days. No electricity required, no fuel burned, no monthly bill attached. And what made it even more astonishing was this. The same thermosiphon principle William Bailey patented in 1909 worked just as effectively with beer cans as it had with copper pipes. Ordinary people realized they could heat their homes using materials headed for the landfill. The implication was staggering, but really, the only thing shocking was how long people had been taught not to notice. Modern science has since confirmed what those 1970s builders discovered with their own hands. In 2019, researchers at the University of Alberta in Canada tested do-it-yourself pop can solar heaters in real winter conditions. Not ideal lab conditions. Real cold. At minus 15 degrees Celsius, with snow on the ground, the test panels still achieved a steady 20 degrees Celsius temperature rise in the output air. During peak sunlight, the panels produced about 1,000 BTU per hour. That is not symbolism. That is not hype. That is measurable. Useful heat pulled out of recycled waste. The National Renewable Energy Laboratory has also documented that dark-colored surfaces absorb about 95% of incoming solar radiation. Flat black paint on aluminum reaches exactly that kind of absorption performance. Commercial solar air heaters priced between $2,000 and $4,000 use the same underlying physics. The same sun, the same heat trapping, the same air movement. The only real differences are branding, packaging, and building code approval. And the material itself tells the story even more clearly. The aluminum in a Coca-Cola can conduct heat at 205 watts per meter Kelvin. That is not a guess. That is not a sales pitch. That is a measured physical property. It does not matter whether that aluminum is sitting in a research laboratory or crushed under coffee grounds in your recycling bin. The physics stays the same. The opportunity stays the same. Only our attention changes. So how does a wall of empty cans actually heat a house? The answer is almost embarrassingly simple, and that may be exactly why it was so dangerous to industries built on complicated systems and recurring payments. Hot air rises, cold air falls. That is the thermosiphon principle. No electricity, no pumps, no moving parts. Imagine a vertical column of aluminum cans with the tops and bottoms removed. Air enters at the bottom. Sunlight passes through the glass glazing and strikes the black painted cans. The aluminum absorbs that sunlight and turns it into heat. The air inside the cans warms quickly. And because warm air is less dense than cold air, it rises through the column and exits at the top. That rising air creates negative pressure at the bottom, which pulls more cool air in. The cycle repeats itself as long as the sun is shining. That means no switches to flip, no buttons to press, no fuel deliveries. The sun does the work while you live your life. Passive airflow rates of 50 to 150 cubic feet per minute can occur with zero energy input. And the glazing is what makes the whole system intensify. What de Saussure demonstrated in 1767 is still doing the heavy lifting today. Shortwave solar radiation passes through glass with ease. When it hits the black aluminum, it becomes long-wave thermal energy. That heat does not escape back through the glass nearly as easily. It gets trapped. Collector temperatures on sunny winter days can reach 150 to 180 degrees Fahrenheit. With insulated backing behind the cans to stop heat from escaping through the wall, that warmth is pushed inward, into the living space, carried by the natural convective flow of air. That is where the real power of this idea starts to reveal itself. Not in fantasy, not in slogans, in basic, repeatable physics that never stopped working. The numbers make the case with brutal clarity. A standard 4x8 foot panel holds roughly 240 aluminum cans arranged in vertical columns. Depending on the depth of the frame, each column usually contains 8 to 10 cans. And that single panel can produce more than 1,000 BTU per hour during peak sunlight. 4 panels mounted on a south-facing wall can provide supplemental heat for a 1,000 square foot home. Material costs, when salvaged lumber and recycled cans are used, fall between $50 and $100. Meanwhile, the commercial equivalent sells for $2,000 to $4,000, while relying on exactly the same physical principles. That is what makes this so hard to ignore. The difference is not in the science. The difference is in who gets paid. But really, the foundation for all of this was laid long before the first soda can was ever pulled from a vending machine. In Geneva, in 1767, Horace Benedict de Saussure built 3 nested glass boxes, each smaller than the one before, each painted black inside. He placed them in the Alpine sun and watched the temperature rise to 230 degrees Fahrenheit, hot enough to cook fruit, hot enough to prove, beyond argument, that sunlight could be trapped, intensified, and turned into useful heat. That was the first hotbox, and really, the principle has not changed since then. Sunlight enters through transparent glazing, strikes a dark surface, converts to heat, and gets trapped inside. Your great-grandparents in Florida used it before petroleum interests pushed it out of building culture. The system did not vanish because it stopped working. It vanished because other systems became more profitable. And now, here it is again, hiding in plain sight. Those crushed aluminum cans in the recycling bin are not just waste. They are thermal collectors waiting to be recognized. Paint them flat black, stack them into columns, seal them behind glazing. Suddenly, they become part of the same heat engine de Saussure, demonstrated back in 1767. The physics did not evolve. It did not need to. What changed was what society chose to remember and what it chose to forget. A 4 by 8 foot panel can hold around 240 cans, arranged in long vertical rows. Cold air enters through the bottom. It rises through sun-heated aluminum and exits at the top, often 15 to 20 degrees Celsius warmer than when it entered. On a clear winter day, that can mean several thousand BTU of free heat. Enough to warm a room in a real, noticeable way. Enough to matter. Enough to reduce what your furnace has to do. And it does all of that without burning fuel, without consuming household electricity, and without involving the utility company at all. The materials themselves tell you exactly who this technology belongs to. Dimensional lumber for the frame, plywood for the backing, foil-faced rigid foam to stop heat from conducting backward through the wall, polycarbonate or tempered glass for the glazing, something transparent that lets sunlight in and traps warmth inside, high-temperature silicone for the joints, flat black grill paint, the kind made for wood stoves, because ordinary spray paint blisters under collector temperatures and glossy finishes reflect the very energy you are trying to capture. Then, for builders who want active assistance, a small 12-volt fan, often salvaged from an old computer and powered by a tiny solar panel. That fan runs exactly when the sun is available and stops when it is not. No thermostat, no complex wiring, no electrician. Just timing built into the sunlight itself. That is the elegance of the design. Every piece serves a purpose. Nothing exists to create artificial complexity. Nothing is there just to force dependence on specialists. You rinse the cans. You punch holes in the bottoms for airflow. You stack them into columns and seal the joints with furnace cement. Then you build a shallow box, insulate the back, and drill the openings needed to hold the can columns in place. At the top and bottom, you create plenum chambers where air gathers and redistributes. Baffle plates, nothing more than simple sheet metal with holes lined up to each column, keep the airflow moving through the intended path instead of skipping around the edges. Because that matters. Airflow is everything here. If the air bypasses the heated cans, performance collapses. And that leads to one of the most important details of all, sealing. The glazing closes off the front of the collector, and every joint must be caulked carefully, because air leaks destroy efficiency faster than almost any other construction flaw. The whole assembly mounts on a south-facing wall and connects to the interior through 2 round vents. Cool room air exits low. Warm air returns high. That is the loop. That is the engine. During the day, sunlight drives it. But at night, there is a danger. When the collector cools below room temperature, reverse thermosiphon can begin pulling heat back out of the house. That is why backdraft dampers matter. And the beautiful part is how simple they are. They do not need to be complicated devices. They can be lightweight flaps held shut by gravity until rising warm air pushes them open. That is enough to stop the nighttime heat loss and protect the gains made during the day. Even the geometry works in your favor more than most people realize. A collector tilted at 60 degrees from horizontal captures maximum winter sun, but a vertical mount often works nearly as well and makes installation dramatically easier. In fact, The low winter sun strikes a vertical south-facing wall more effectively than intuition suggests. And in summer, when extra heat is the last thing you want, that same high sun angle barely touches the panel. Some builders go one step further and add a simple overhang to block summer sunlight almost completely. A few dollars in lumber turns a possible overheating issue into a non-event. The seasonal math is almost poetic in how perfectly it aligns with real need. In the northern hemisphere, winter sun angles can drop as low as 20 to 30 degrees above the horizon at midday. A vertical collector mounted flush on a south-facing wall captures that low-angle light with remarkable efficiency, sometimes outperforming tilted panels designed more for summer exposure. Then the seasons turn. Summer sun climbs to 70 degrees or more, and the high angle glances off that same vertical surface, naturally limiting heat gain during the very months when people are running air conditioning instead of furnaces. This self-regulation is built right into the geometry. No engineer had to invent it. The Earth's axial tilt was already doing the work. Construction simply had to catch up, and once that warmth enters the house, your home itself becomes part of the system. Thermal mass changes everything. Concrete floors, brick walls, even heavy furniture absorb heat during the day and release it gradually after sunset. In a well-insulated house with enough mass, the effect of afternoon solar collection can linger deep into the evening. Lightweight homes warm up quickly, yes, but they also let that heat go faster. So knowing the character of your own house tells you what kind of results to expect. The collector is only one part of the equation. The building receiving the heat matters too. Climate matters as well. The sunny but bitterly cold Mountain West can produce excellent results because the skies stay clear even when temperatures plunge below zero. The Pacific Northwest, with its long stretches of cloud cover, sees reduced output, though diffuse light still contributes something. Desert climates receive intense sunlight, but often do not need much supplemental heating in the first place. The real sweet spot lies in places where winters are cold and sunshine still arrives regularly. The upper Midwest, the Northeast, the Rocky Mountain states, parts of Canada, places where heating bills hurt the most. Places where a simple box filled with painted cans stops being a curiosity and starts becoming a serious tool. That is when this stops sounding like an interesting project and starts looking like a direct challenge to the systems people were told they had no choice but to depend on. The economics behind this are where the story becomes impossible to dismiss. The Energy Information Administration reports that the average American household spends roughly $1,200 each year on heating. 4 panels producing about 4,000 BTU per hour during sunny winter periods can offset somewhere between 15% and 30% of that demand. Think about what that means. A system built from $50 to $100 in materials can pay for itself in a single heating season, one winter. Compare that to commercial solar installations that often need 10 to 15 years to break even. And here, there is no fuel truck coming down your road, no electric meter spinning faster, no monthly bill attached to every sunrise. The operating cost is permanently zero. Maintenance is almost laughably small compared with conventional heating systems. Repaint the collector perhaps once a decade. Replace the glazing someday if you chose the cheapest material. That is about it. No technician visits, no annual service contracts, almost no moving parts to fail, no burner assemblies, no heat exchangers, no expensive control boards. You become the technician because the knowledge stays with you. And that is exactly what makes this kind of system so disruptive. Dependency begins to dissolve the moment. Ordinary people understand how little machinery is actually required to turn sunlight into warmth. Durability comes down to a few choices made during construction. Aluminum has one huge advantage over steel. It does not rust. That alone gives can-based collectors a longer life than many improvised metal designs. Glass can last indefinitely, but it brings weight and the risk of shattering if struck. Polycarbonate twin wall panels handle impact better and provide stronger insulation, but they can yellow after 15 to 20 years of ultraviolet exposure. Greenhouse film costs almost nothing, but usually needs replacement every 3 to 5 years. Every option comes with trade-offs. Serious builders often settle on polycarbonate because it balances durability, insulation, and moderate cost, even if eventual replacement has to be planned for. Then we arrive at the silence. And that silence says more than any advertisement ever could. Building codes largely ignore this technology. But really, that omission reveals how construction regulation often works in the real world. Code committees are heavily populated by people tied to HVAC manufacturers, licensed contractors, insurers, and the industries that profit when heating systems stay complicated, regulated, and professionally installed. Approved heating technologies create jobs, recurring revenue, inspection chains, liability structures, and permanent dependence on established suppliers. But a heating collector that a homeowner can build from recycled aluminum, salvaged wood, insulation board, and a transparent cover has no giant manufacturer behind it, no lobbying budget, no sales team, no campaign to secure code inclusion. So it gets ignored. And really, that silence is not random. Look at what receives tax rebates and utility incentives. Grid-connected solar electric panels often qualify. Why? Because the grid still benefits when you install a system that feeds power back into infrastructure they control and can resell to your neighbors. But passive solar thermal, the kind that simply lets you stop buying a portion of what they sell, receives almost nothing. That distinction matters. The grid profits when you stay connected. It does not profit when you quietly reduce demand with a collector mounted on your own wall. Incentive structures reward technologies that preserve the relationship. They neglect technologies that loosen it. Follow the rebates, and you follow the money. Every BTU you collect from sunlight is a BTU you do not purchase from a utility, a fuel oil supplier, or a natural gas provider. Passive solar does not threaten physics. It threatens recurring revenue. And that is the entire issue. This is not some dramatic conspiracy theory that needs fantasy to survive. It is economics. Technologies that erase ongoing payments rarely attract serious investment because there is no endless stream of billing attached to them. They do not generate dependence. They do not create subscription-like revenue. So they are not aggressively promoted. They are not pushed into codes. They are not handed flashy campaigns. They are quietly forgotten beneath more approved, more expensive, more professionally mediated alternatives. But none of that changes the one thing that cannot be negotiated away. The sun still delivers roughly 1,000 watts per square meter and asks for nothing in return. The same physics demonstrated in Geneva in 1767 still works in a backyard, on a garage wall, or beside a shed. Aluminum painted flat black still absorbs around 95% of incoming solar radiation. Hot air still rises, cold air still falls, glass still traps heat. Insulation still keeps it from escaping backward. That chain of truth has survived every code revision, every market shift, every lobbying campaign, and every generation taught to look past the simplest answer. And there is something deeper in that. At Yazd, Persian ice houses still stand after 2,400 years. De Saussure's hotbox principle still warms greenhouses across Scandinavia. Your great-grandparents knew these systems worked. Families in Florida and California once used them openly before a different economic order took over the building culture. The science was never lost. What changed was who profited from your forgetting. Now the blueprints are everywhere. Builders have refined them online over decades. Forums are filled with people who measured real performance, tested different layouts, compared glazing materials, experimented with fan assistance, and documented what happened in actual winter conditions. The materials are still cheap, in some cases almost free. The skills required are not mysterious. A patient person can learn them in an afternoon. Clean cans, cut airflow openings, seal the joints, build the box, insulate the back, glaze the front, mount it where the winter sun can strike. That is not industrial magic. That is practical knowledge. And those